Alright guys, we're going to pick up where we left off. When I start this video, two things that I want to make sure that you remember from the last video is that by graphs, this equaled 1 and this equaled 0. Okay? So what you're going to try to do is you're going to try to find forms of these, and you're going to create forms of those amongst all of these problems. Okay? So you could see something that looked like sine of y over y as y is approaching 0. Anyone? What would that equal? 1. It could be sine of PHS over PHS. If PHS is approaching 0, what's this? 1. Okay, understand that those are the variables, because I want you to find those today. How about if it was approaching infinity? Would it equal 1? No, it's a different type of problem, okay? So the stipulations are they must approach that. Okay, so let's look at this first example. I have sine of 5x over 5x. If I plugged it in right now, I would get 0 over 0. So we have to do some kind of algebraic manipulation. Okay, let's try to find a form of this. Well, there is a form of that. I have something over the same thing. And the biggest mistake people make is that they say it cancels to 1. They say that this cancels with this to 1. And they're wrong, because that's not canceling. Okay? Canceling would be this. If you had like 5x, let's say y cubed over 5x, this would cancel as a form of 1 to give me that. But this is not the same thing. The reason why is because those people who make that mistake, what do they think exists between sine and 5x? Multiplication. But it doesn't. Sine of 5x is the same as what we've talked about in years past. F of x. There's no multiplication. I know a lot of you know this, but I want to make sure the ones that don't are refining it right now. Okay. So this will become 1, and there's my answer. There's no algebraic manipulation that has to be made. We just have to remember we applied this special trick. Okay? The other one is sine of 5x over 4x. Obviously, I can't do that right now because these are not the same. I cannot use this limit that will equal 1. Any suggestions? What should I do? We're going to algebraically manipulate this because ultimately we want to see if we can cancel this x on the bottom some way or somehow. Because that's the only thing that's making this whole thing undefined right now. Any suggestions? Okay, so I'll start. We're going to multiply by a form of 1. And the form of 1 that we're going to multiply is so that we can thereafter use that rule that we just learned up here. I'm going to multiply this by 5x over 5x. And the reason that being is you should be able to identify, you should be able to see right now that ultimately this will become 1 when the limit is applied. Again, it does not cancel to 1. It will become 1. So in your work, I want you to show that it's becoming 1, not show that it cancels to 1. Alright. So I just multiplied by a form of 1. And get this. I'm going to now cancel this piece and this piece to what? To 1. X over x will become 1. You with me? So here we go. I'm going to write on the top 5 times the sine of 5x over, those x's cancel to a form of 1. So I'm left with 5x, and this 4 is still there. Multiplication, multiplication, multiplication. What was the thing that I did? What all did I do just now to get from this to what I have now? All I did was cancel the piece that would otherwise have made the denominator 0. You just cancel the piece that made the denominator 0 originally. What are you going to do next? You're going to plug in your value that you're ready to do. You with me? Here we go. When we plug in, what will this become from what we just learned? 1. Don't cancel it to 1 early. If you do, you miss that problem because you don't understand when to apply the limit and what it will become. You need to know that difference between when do things cancel to 1. You with me? Okay, we're going to do some more. So, guys, what will this become at the very end? 5/4. So, this right here is the total answer, and this right here is the most simplified form before you plug it in. You with me? Okay. So, if you have this form, it tells me you did everything else right. Alright, so let's move on to the next example. I have 5 times sine of 2x over sine of 3x. If I plugged in 0, which should always be my first go-to, anyone, what would I have if I plugged in 0 right now? Sine of 0, what's sine of 0? 0. So I would have 0 on the top and I would have 0 on the bottom. Because of this, we have to do some algebraic manipulation. Okay? So here we go. Let's multiply our stuff by a form of 1. There's this algebraic rewrite. What form of 1 could I multiply this by? Anyone? 2x over 2x. Perfect. Because you're already identifying from that rule that we just learned today that there's my piece that will become 1. Please do not cancel it early to 1. There's a difference between canceling to 1 and it becoming 1. Now, will this become 1? No. So what else could we multiply by a form of 1? What could we do? Say again, I can't hear you. Any suggestions? We could either do 3x over 3x. Don't write this down yet. We could do 3x over 3x because there's my piece that would become 1. Because here's another rule I want you to write down. Just like you wrote the sine of theta over theta, if theta is approaching 0, is equal to 1, the other rule is true of the reciprocal of this. Also will become 1. Okay? So, yes, you could multiply by 3x over 3x and then cancel these x's to 1, or you could have just multiplied by what over what? 3 over 3. 3 over 3. So if I did 3 over 3, check this out. Oops. Let's do 3 over 3 multiplying by a form of 1, because look, there's my 3x. That with that 3x would become this form of 1. Y'all with me, guys? Notice I'm not canceling those pieces yet. The only pieces that I could cancel if I needed to right now, I'm going to highlight in orange, would be the 5, 2, and 3. Those are the only pieces that I could cancel. Everything else will become 1 once I flip that switch. Otherwise, throw in this value of 0 of the limit. That's called applying the limit. Are we good? Okay, so is this my most simplified reduced form, yes or no? It is. Well, no, it is. It is. There's nothing else that I can cancel right now to 1 or a form of 1. You with me? This is the most simplified form. Because when I turn the machine on, what will my answer be? 10 over 3. Because you get it from 5 times 2 gave you that 10, and this 3 is still remaining. Everything else paired up and became 1. Yeah.
So why wouldn't it be 10x over 3 if the 2 still has the x?
Okay, the 2 still has the x, but multiplication does not have order. So 2 times x times 3 could be this times 3. It could be this times 3. It could be, or sorry, times 2. And it could be this times x. So the x is not glued to 2x where it has to stay with it. It can move because multiplication has no order. Okay, really good question. Let's move on to the next one. The next one has a fraction. Let's talk about this. We need to refer a lot to 5th grade, okay? Make things easy. We learned in 5th grade that if I have common denominators, and only if I have common denominators, I can add or subtract fractions to combine them to be 1. Like this. Now what we're doing in calc is all this algebraic manipulation, we have to go backwards a lot. You with me? So when you see one huge function that almost looks like a rational function, what we want to do is we want to break it up into simpler things like in 5th grade. So that would be like 2x over x plus sine of x over x. And we're going to take the limit of all of that. Here comes one of the limit laws that we had. A limit of the sum is equal to the sum of the limits. So that means I want to first evaluate what this one is. Let me see if it'll let me copy. Yep. And then I'll do the other one. Okay, so let's find the limit as far as 2x over x. We'll find the limit as sine of x over x. And whatever we get here, we're going to add with whatever we get here. Remember, this is not distribution. It's applying the limit to both. It looks like distribution, but it's applying the limit to both. Okay, so anyone, can you please tell me, what would I get for this first one? Okay, before we solve 2x over x, what should we always do right before we plug in the limit? We should always try to do what? Cancel and simplify. Can I simplify 2x over x? To what? To 2. So imagine x is approaching 0 of 2. What's that answer? Just 2. And if you need a visual, quickly graph y is equal to 2. And if you approach 0 from the right and left, you know that it's going to limit out at the value of 2. Now, we just learned it. What does this equal? 1. So, look, this will become, you could either write it like this, and then put 2, or you could just still leave it as this, and then at the very end, what would you write as your final answer? 3. And do it like that. You with me? Yes, if you wanted to do it individually and say that you got 2 and you got 1 and showed it like this, I would still accept it. But I'm trying to find out, did they know what the most simplified forms were before plugging in the limit? And if they did, and you can show that, you're good to go. You with me? And the steps are the same all the time, guys. Different algebra, but the steps are the same. You're trying to cancel that piece that otherwise would make it undefined. And at the same time, reduce before plugging in. Reduce before plugging in. Okay. So let's look at, we're going to squeeze through them for now. I think because of the sake of time, we might even take it off the test. We'll see. Let's go over to more practice. I want you to get acclimated with this to be able to do without the calculator. So our function is 1 over x plus 3 for days. Okay? So if I graph that, it's, guys, if you don't remember parent functions, you're going to have to recall that information very quickly. And I'm talking about x squared, square root of x, natural log of x, 1 over x. All of these different parent functions, we have to know what they look like default-wise. Because this is a shift, how many units, what direction? 3 to the right. Because remember, when it's with the x, we always do the opposite, right? could say ex-girlfriend, ex-wife, whatever, ex-boyfriend. You did the opposite. That's why they're your ex. So with that, we're going to shift it 3 to the right to where this graph would look something like this. Because there's a horizontal asymptote at y is equal to 0, and there's a vertical asymptote where? At x is equal to 3. So now, these questions are easy, and they're cake, because you have to ask yourself, remember that acronym we talked about on day 1, is it easier for me to answer this if I graph it? Is it easier for me if I try to use table? Or is it easier for me if I use algebraic manipulation to do all these limits? And the graphs tend to help a lot. Okay? So anyone, what's the answer for A? Negative infinity. What's the answer for B? Infinity. What's the answer for this one? Does not exist. And what I want you to do, actually, let me just say, what do we call this limit? There was a term that we had for it. Not the jump discontinuity. Maybe I didn't mention it. This is the general limit. These are one-sided limits. Remember, the biggest thing is if the one-sided limits, if this equals this, which in this case it does not, then the answer is D and E. But if they do equal each other, then it's whatever those numbers were. They made that ET moment. You with me? So one-sided limits versus general limit. So guys, if you can find the general limit, can you find for sure both one-sided limits? Yes? How about if you can find the one-sided limits? Does it guarantee that you will be able to find the general limit? Well, the way I worded that was a little confusing. It will guarantee that it will either equal that number or B does not exist.
Right.
Yeah.
So will there ever be a question where you have to find, like you have to do algebraic manipulation and the answer does not exist?
Yes. Yes. It's very rare. It's cool stuff. I don't think you'll see it today. Okay. All right. Like not for the test, is what I'm saying. Not for the test. All right. Yes, and it is cool. So as far as this graph is concerned, the parent function of this one is very close to this. Okay, so real quick. The only difference is, whoops, this squared, think about it conceptually. This squared means that you'll never have a negative answer, because two negatives make a positive. So what that means is this piece now becomes positive, so that my parent function of 1 over x squared, which is another one that we should kind of memorize, will look like this, where all positive values only exist. Now we're going to shift it 3 to the what? To the right, because it's with the x, we're doing the opposite. So here's your vertical asymptote, 1, 2, and 3, and the graph would look like this. So guys, what is the answer to this limit? Infinity. Because the right side, one-sided limit approach infinity, and the left side approach infinity. Now, I want you to put this on the test. I want you to put this on the AP exam. But how would you answer this in a college class? Does not exist. We just say how it does not exist. Okay? All right. Because if we put D and E, we're talking about that they approach at different ones. That's our way of showing D and E. Okay. Let's go to this example. Now we talked about this function last time. And I even showed the long wave process to show this. The way I want you to see it quickly is if these are the same, you know they're going to cancel to a form of what? 1. Positive or negative 1. So this right here is the positive or negative 1. Okay? So you don't graph this just yet. You're going to have this. You're going to have branches of this exist with this jump discontinuity. this part right here, our denominator, cannot be 0. So where would that jump discontinuity exist? At 2. So I'm going to come to the graph, and at 2, I'm going to put open, open. And our graph will either do this, or it will do this. It won't do that, because that doesn't even pass the vertical line test. Okay, so we just have to pick any arbitrary point and plug it in just to see what is our answer going to be. So anyone, pick an x. 4. So if I put 4 into the original equation, 4 minus 2 is 2, the absolute value of that is still 2. On the bottom, it would be a positive. So wherever 4 is at, it's positive. That means it's above the x-axis. So our graph will end up looking like this, and everything else gets erased. Remember, it's open at 2. So here and here.
When you plug in a number, it determines the top.
When you plug in a number, it determines,
So
yes.
plug in 4 and
Well,
it's positive.
not necessarily the top. That's a really good question. Because what if I plugged in 1 or 0? If I plugged in 0, the top would be 2. If I plugged in 0, the bottom would be a negative 2. So my negative answer would occur at x is equal to 0, which makes sense. So whatever you plug in doesn't determine the top, it determines the leg, if it's going to be a positive or a negative. Alright, so now looking at this graph, guys, what's the answer to E? Negative 1. What's the answer to F? Positive 1. What's the answer to G? Does not exist. Because those two one-sided limits did not equal each other. Whew. Yes?
How did you decide that the lines were going to be at 1?
Oh, because these pieces cancel to a form of 1. That's a really good question. Will it always cancel to 1 or negative 1? No, because you could have a number in front of this. It could look like 3 times x minus 2. So now this won't be 1 and negative 1. It will be 3 and negative 3. Because it's like a vertical stretch. We good? Okay. Now, it didn't print off on this. That's why we're going to go over it. The greatest integer value function is the step function. And it has brackets like this. Okay, so this step function is the following. Let's say that I have 0.1111, and then I have 1.1111. So, let me ask you. What's the greatest integer that 0.1111 used to be? Let me say that again. On a number line, here's 0, and here's 0.111111, real close to 0. What was the greatest integer that 0.111111 used to be? 0. It used to be 0. What was the greatest integer that 1.1111 used to be? 1. So the graph will look like this. So this is 1, this is 2, and this is 3. Okay, you with me? For instance, let's try 2.111111. What was the greatest integer value that it used to be? It used to be 2. That's why, guys, on the graph, if it used to be 2, it would be 2 right here on the y-axis. This is why this would be 1 on the y-axis. Are you with me? Do you understand the graph? So, yeah, some people don't. So -1, -2. Look, the graph will continue to do this. And then I'll give you some test points so you can understand why it works. Okay, so let's go down 1. And we're going to put an open line closed. Okay, then we'll go down to -2. And we will put an open line closed. Dylan, I want you to pick any number between -2 and 3. No, not an integer, but like with point, whatever. Okay, so 1.111, this one right here. If I were to find it on the graph, on the x-axis, it would be right here. Do you agree? So let's jump on the graph. What's the y value right there? 1.
The thing I'm confused about is, like, the graph is just x minus 2, so, like, that's the function.
I know. So to me, remember at the very beginning, I told you that it didn't print off. You need to physically write these brackets in, because the function should have said and should have been listed like this. That's a greatest integer value function. It comes from the parent function, which is that. Oh, that's why you're saying you're confused, because I haven't shifted it yet. Okay, so listen, nice observation. Thank you, Dylan. What I just graphed right now, was this. Okay, nice job. That's what I graphed. But if this is a horizontal shift 2 units to the what? To the right, I need to graph the correct graph. Okay, so real quick, no worries. This is actually a good mistake because it does strengthen still the horizontal transformation. It would look like this. So it's the same graph, but only shifted 2 to the right. So where 2 starts here, it would go to 3 as an open. So 1, 2, 3. Then it would jump up, bless you, to our first y value. Bless you. So let me keep going with this. Here's 4. Here is 2. Okay? And if I were to, this is -1. Thank you, Dylan. This is -2. This is -1, -2. So let's keep going. Let me do it in purple so it sees a little bit better. So open, closed. Jump up, close to open. Jump up, close to open, so on and so forth. Then jump down, open to closed. Notice how they're just one integer away. Open to closed. And then open to closed, so on and so forth. So this graph has been shifted 2 to the right, which is exactly what we saw from here, shifting 2 to the right. Nice catch, John. Thank you. Does it make sense now? Okay, so good. Let's go to now this graph to answer these limit questions. Let's approach 1 from the left. Anyone, what's the answer? -2. Approaching 1 from the left. Let's approach 1 from the right. -1. What is the general limit equal? Does not exist. How's that? Everyone good? Okay. So let's go now to more algebraic manipulation with this example right here. Someone was excited. All right. Sometimes you need to use the properties of limits to make the problems easier. Sometimes you can draw a sketch. So this one has 2 functions in one, and we're gonna we're going to figure out what's going on, okay? So first of all, this is a graph that will simplify to positive and negative 1. Remember that? So if we're doing this, this is a product. Our limit law said this. The limit of a product is equal to the product of the limits. Meaning we can break these limits up if we want and then just multiply their answers together. So let's go ahead and write that out. So the limit as x is approaching 2 from the left, we're going to break this up twice and then we're going to multiply those answers, whatever they end up becoming, at the end. So let's do it for x cubed, and let's do it for this removable discontinuity function. You with me, guys? Here we go. X cubed, we know what that looks like. Looks like this. We can do what we did early in this video as far as plus or minus 1. You with me? We know that the removable discontinuity is going to occur at 2. Now I just got to find out, what are the legs doing? Are they going to go like this, or are they going to go like this? Okay, so let's plug in a point. 1. If I plug in a point 1, I get a positive over a what? A negative. So at 1, it's a negative. So that means at x is equal to 1, it will be below, and the other leg will be a positive. Okay? So now, here we go. Let's approach 2 from the left. What's the answer to this limit right here? Negative 1. Let's approach 2 from the left. I get 8. And 8 times the negative 1, what's my final answer? Negative 8. Do you see how we're using limit laws to make it easier? Do you see how we're using forms of 1 algebraic manipulation to make it easier? And graphs, for sure. You good?
Yeah.
Okay. Let's keep going. We don't need to do this one. Let's keep going. Alright. Be careful when you apply the limit properties, because if this approach leads to a result that's 0 times infinity, it does not help determine the answer. Okay? If you get this, you got to keep working. Something's wrong. This goes back to the question that Dylan was asking. Can you ask that question again? As far as he said this, when you do algebraic manipulation, can you still get a does not exist even after you cancel that denominator? Okay? So look, if you get a 0 over 0, do some more work. There's still work to be done. If you get infinity divided by infinity, do some more work. There's still work to be done. And if you get this, it doesn't necessarily mean you're done, because 0 times infinity is not 0. 0 times infinity is not infinity. It's indeterminate, and you'll learn it later this year. Not right now. They're indeterminate forms. These are the 3 that you will learn this year. And you're going to learn it with the proof of a mathematician. His last name was L'Hopital. It looks like a hospital, but it's L'Hopital's rule. Okay? La Hospital. So, I don't know. Anyway, so let's go to let's go to this example and see what we're talking about here. If I plugged in 3 right now, I would get a 0 over 0. So I've got to do algebraic manipulation. So x minus 3, x plus 2, factoring was one of the algebraic manipulation forms that we learned. because our goal was to try to cancel out the what? The hole in the graph, the removable discontinuity. So that all you're really left, good, remember I keep saying the same things. Cancel or reduce, simplify your life before you plug in the limit. We just canceled that piece that would otherwise have made this an undefined sort of. So our most simplified form that I keep going to is if you can get here, it tells me you've done everything correct. What would I plug in? Just 3. And I would get what? 5. Done. All right. Let's go to let's keep going. I'm trying to touch more on the ones that are more representative of the big concepts, okay? All right, practice. If I plug in 0, I'll get 0 over 0. Go with me? So I have to do some form of manipulation. So let's distribute. Actually, you know what I'll do? Just so you can see it better. Sometimes you got to make it a little bit more involved before it simplifies out. So I just distributed this. The number one, every year, students struggle with this. Okay? They say that this is equal to that. And then some people will be like, no, you got that wrong because you forgot that a negative times a negative is a positive. And they're still wrong themselves, right? So this is equal to a multiplicity of 2, which means you've written it out twice and distributed it or FOIL. Or box method, however you learn. Please, common mistake, let's master that. So now, you'll see me saying this all year. Cancellation of a form of what? 0. Okay? Cancellation of a form of 0, which leaves me, whoops, with this. Can I cancel reduce even more? Yeah, I can. Because I could break this up. Remember, just like we saw today, the backward process from 5th grade? I could break this up and then reduce each piece so that I would get this. You just canceled the piece that would have otherwise made this. Or you could also do this. Some people will go from here, they'll GCF the top. And if you like it, go for it. But I'm telling you, whenever you integrate this, you're going to use a lot. So don't dismiss that, okay? All right. So what's my answer, anyone? Negative 10. Okay, you're getting a lot of algebraic manipulation under your belt. And at the end, I'm going to ask you to... Okay, so what we're going to do, guys, and this is most likely going to be like an extra credit for your test. Remember that Flipgrid that I was talking about that you signed forms for, right?
Yes.
The Flipgrid is basically, it's like a social media platform for education to where you are recording your own explanations or whatnot through video. And here's the thing, you're building a video diary. Don't ever be afraid of being incorrect, because a lot of people, everyone's going to be able to see your video and they'll be able to comment on it or not comment on it. So yes, I will look at videos, and as we get more and more with this, the better videos will get more bonus points, because more you can like other videos, and please don't just like your friends, but like the ones that make sense, okay? And I will also see the videos. But here's the thing, ultimately, you're going to be able to go back after Unit 8 and be like, how did I used to think about limits? And you can hear how correct or incorrect you might be. You know what I mean? And your develop of understanding will increase as you're doing this, because it's forcing you to do that metacognition, that thinking about thinking. Okay, and that's a huge thing. And if you can do it, you're strengthening yourself each time that you do it. It's like reflecting on, what am I doing right now? Why am I doing this? How does this work? You know what I mean? That slow pause for pause is what makes you strengthen your metacognition. Metacognition is huge. I've always thought metacognition is huge. Lately, it's a new buzzword that a lot of teachers
Yeah,
have stolen.
I've had 3 teachers this year, including you, talk about metacognition.
Yeah, because I mean, it is true, because if you can relate where you're at, if you can find where you're at, you know how strong or weak you are. But if you have no idea, and you're just, like, let's say I walked in this room and the lights were off, and I have no idea where anything is at, you're lost. Like, you can't measure where you're at. So that metacognitive tool is just that. Now, let's do some practice, because this is similar right here to that number 5 on your quiz that I think only 2 or 3 people got correct, right? So, this is similar to that problem. Oh, I know, right? So this is similar to that problem that we did. I'm going to teach you a shortcut. What I showed you before is that you could multiply this top by 4 over 4, right here. And you could multiply this top by 4 plus x over 4 plus x, right here. So that you would get, listen, a common denominator in the numerator. Because remember, this is all over x. You with me? But there's an easier way that will get you to the same answer. If you can figure out what is that common denominator, which in this case is what? 4 plus 4x. Whoops, that's not 4 plus 4.
16.
You could do 16 plus 4x. But remember that I told you never distribute the denominator? You'll see what I'm talking about here in just a bit. I'm going to multiply this whole thing, the big picture, with 4 plus x. 4 plus x. It looks like a lot at first, and you're like, that's not easier. It is, okay? You just have to know how to reduce fractions. Will you ever distribute that? The answer is no. You don't want to distribute that. But what's in the numerator piece, you do definitely want to simplify. Okay? Something that you learned in Algebra 2 is that what we just did is we established, look, right here, this is the LCD of these two denominators. It's the least common denominator. So if I distribute that on the first fraction and the second fraction, what reduces is the question that I'm asking myself. Okay, here we go. Think of 4 plus x, this thing right here, we're going to distribute across here. What piece just canceled to a form of 1? 4 plus x. So 4 is left over in the numerator that I will multiply with this 1 in order just to get 4. Okay, let's do this again. We're going to now distribute this piece to the second fraction. What just canceled? 4 over 4. What's left over is 1 times 4 plus x. We just have to remember that this subtraction is still going to occur right there. Y'all with me? Okay. On the bottom, we never simplify. We still have this multiplying together and the whole thing multiplying together. That's not a function composition. These are multiplication pieces. Okay. So what form am I going to, what you just saw happen, what form is going to happen first? A cancellation of 0 or a cancellation of 1? A 0. Cancellation of 0. We're going to concentrate that in the numerator. So look at this. 4 minus x we'll be left with this, and we still have, oh man. Alright, so we still have all of this. Now, what form of 1, oh, I just told you, it's going to cancel to a form of 1, x over x. So that you become negative 1 over 4 plus x. Remember, never simplify the bottom. And yes, I would, if I were you, go back, because I will count off points if you don't write this every single time, because a limit is different than a function. You can't just change a limit problem to a function problem. Okay? This is what I'm looking for, guys. I'm looking for this because if you got to here, it tells me that the answer that you get here is correct because you were able to get to the most simplified form before you derived. This is that you just canceled out the piece that otherwise would have made it undefined. What are you going to do next? You're going to plug it in. Anyone. What do you get for a final answer? Yes, negative 1 over 16. And I want you to write it like that. Yeah.
So how does the negative on the x stay? How can you cancel the force?
Because x and x will cancel to 1.
The negative on the top x, why does that stay?
Because I didn't cancel the sign. I only canceled a positive x and a positive x. Otherwise, it's like saying negative x over positive x.
No, I meant from the step before. From the 4 minus 4.
Oh, how did this show up to begin with? Guys, this is the number 1 mistake. And I told you, number 1 mistake is negatives. Number 2 mistake, parentheses. And this right here is the most common mistake right here that I'm highlighting. The distribution to that second term or that third term or whatever, you have to distribute that negative across the entire binomial, polynomial, whatever it is. Good stuff? Okay. No worries. All right, here we go. I'm gonna go through a couple of these, and then I think I'm gonna actually print off an example, like an activity of some of them, and I want y'all to do this activity together here in just for practice, okay? But real quick, observation. We're trying to identify what's the fast way to solve this limit. So your choices are do the algebra, do the table, or do the graph, okay? Because we're not really doing verbal, okay? The verbal is going to be your Flipgrid. That's you, and you can have a whiteboard at home. You could do whatever you want, but I want you to show where the camera can see the problems that you're doing, and you're basically teaching someone who's never seen a limit, per se. This is what you want them to do. Look, you'll identify that this has a square root. So here's an example, okay? And if you want to record, that's fine. Right now, if you want to record an example. This right here is a limit that involves a square root. Our goal is to cancel this square root, almost like we did with rationalizing denominators. So this wouldn't be a graph. This wouldn't be a table. This would be algebraic manipulation. And the reason of that is because I can multiply by the conjugate, which would be 25 plus x, 25 plus x, but instead of a minus 5, it will be a plus 5. That's your best approach. Because, and then you could just go off of that, guys. You could go from there. Showing them that the algebra of foiling these top two pieces, you will distribute the numerator. You will. Because those cancellations happen to go to what number? 0. The numerator distributions and all those cancellations will ultimately go to 0. What you have left over at the very end will have a cancellation to a form of 1 that gets rid of that x. You with me? Questions? Okay. Real quick. Algebra, table, or graph? Algebra. What do you do algebraically? Factor the top and factor the bottom with sum of cubes. You cancel out the removable discontinuity, and go from there. Now, I'm not actually going through the work. On your Flipgrid, you would go through the work. Like, you'd go through the problem. And you could already have it done. You could already have it done and just point. You're going to go here, you're going to go there, and this is what it's going to look like. You see what I'm saying? Okay. Here we go. Let's look at this one. Algebra, table, or graph? So, some people might do algebra and see that these are going to be that plus and minus 1. Some might go for a graph, still kind of with that algebra per se. But this, we learned it today. What should you do first before looking at that? You should split it. Use limit laws. The limit of this product, there's multiplication there, is equal to the product of the limits, breaking it up. And you're explaining this in the video. If you can explain it simply, you know it well enough yourself. If you can't, and you are even confused of your own video, like you have some metacognitive strategies to work on, right? You got to practice, okay? And this one right here, I believe, yeah, or not brackets, but just it's this. Ooh, it's a duplicate. I think it should be to the from the right. You know what I mean? So that it's a different question. Just sometimes whenever you convert to PDF, it doesn't go. All right, here we go. What form? You have A, N, or G. What form? A, algebraically, right? What does N stand for again? Numerically, which is tables. Okay. So this is an algebraic. What's the strategy? Factor the bottom. This one I will show because we learned it today. So 5x minus 8 could we break this up into a multiplication of two things? Yeah, you can. Because multiplication occurs right here. So you could, if you wanted to, break this up because the limit of a product is equal to the product of the limits. And this would result with, alright, so what will this equal? We learned it today. 1. And this is a good way to show work too as well. You see what I'm doing right now? I'm breaking it up. Whereas the other one, I was highlighting pieces and telling you, oh, that will become 1. But you can always break it up too. Anyway, what would this become? Negative 1 over 8, right? So what's my final answer? Negative 1 over 8. Right? Don't confuse, guys. Just because I put 0 here doesn't mean the whole thing zeroes out. I think some of you were looking at it like that. It will make that 0 minus 8, which is a negative 8. Alright. Now, algebraic.
So the x basically only affects that one constant that it's connected to and leaves everything else alone.
The x is only affecting this one. Yeah.
Yeah, so like if you were to plug in like on the right, if you were to plug into 0 to the x, it only affects the 5, so that's why you get 1 over 8.
Correct. It only affects the 5, not the entire denominator. And that's a common mistake. That's why I was saying, like, people make that mistake.
So like if it was a 2, you plug in, you get like 1 over
1/2.
negative.
Yep. And I know that seems like duh, but it's not duh. Like, I understand that struggle because when you plug in, especially when there's square roots in the denominator, you're like, what's going on? You know what I mean? Like, anyway, so let's look at this problem right here.
Oh yeah, we did this one earlier.
We did it algebraically. Okay, let's show algebraic manipulation because your work is going to be what's getting you points. Because the answer, guys, is just 1 point to maybe 5 or 6 for each question. Some of them are even up to 9 and 10. So the point is the answer is 1 point of 10. All of your work, especially with neat work, is all going to be, you know, the big parts of your points for each question. So, here we go. Algebraic manipulation. Help me out. What's the first form of 1 that I could multiply this by? 2x over 2x. Because some of you already see it. That will... Is that 1 right now? No. But it will become 1 when I plug in the limit. Okay? is this one right now? No. Okay, it's got to be an exact carbon copy. What form of 1 could I multiply right now? 3 over 3. Because, like we were saying earlier, whoops, let's do it like this. Like we were saying earlier, this can be grouped because multiplication has no order, and that will become 1. So the only things that are not accounted for right now, is this the same exact problem?
Yes.
You're going to get 10/3. Now listen, look, some of you will see this and you'll understand and you'll do this. And all this will give you all kind of full value points. 1 point here, and then the rest with that algebraic manipulation. The limit of a product is equal to the product of the limits. I can, from here if I wanted to write out the limit as x, and I'm curious to see how many people do this. And that's okay if you do. Oh man. So the limit and you would have sine of 2x over 2x, sine of 3x, 3x, and then you would have 5 times 2 over 3. And you're going to be multiplying these together. Okay, so it said originally that the limit of these products is equal to the products of the limits. So you could figure out like this, and this is going to be, like if you do this, this is good. This is real good. Like, what is that going to equal? 1. What is this? 1. What is this? 10/3. And you could show this work and be very organized and still get 10/3. Good stuff? All right.